the meeting that is going on now at the Perimeter Institute on experimental search for quantum gravity, the hard facts. So I think that this is very important to keep a good, solid connection between quantum gravity, which often tends to be somewhat detached from experiment or observation, and the so-called hard facts. So you should remember that physics is an experimental science. Okay. So the outline of my talk is as follows. I would start with some brief motivation, although I probably don't need to spend too much time to motivate this crowd. And then I would unfortunately need to narrow down the scope because the astrophysical tests of quantum gravity is way too wide even to cover in an hour. So just briefly mention some of the things that can be tested, and then I'll talk in a bit more detail on some more specific topics within the subject. In particular, I would talk about vacuum birefringence or helicity dependence of the photon propagation speed, in addition to vacuum dispersion or energy dependence of the photon propagation speed, to which I would devote most of this talk because that's where I did most of the work in this field. So I can talk about it more. In particular, I would talk about how we can constrain using astrophysical observations vacuum energy dispersion. In particular, I would briefly describe how this was done using TV flares from active galactic nuclei. And then I would describe in much more detail the work that I was involved in of constraining this using gamma ray bursts. I would try to explain why gamma ray bursts are so useful for that and how use them to set our limits, or hopefully maybe detect something in the future. I would then mention an early limit we got from the long duration gamma ray burst 080916C, redshift of about 4.3, and devote more time to the more interesting short gamma ray burst 090510, which is at a slightly more modest redshift of 0.9, but being very bright and much shorter could give us much better limits. So I would talk in more detail about that, and I would summarize all the limits we got using the Fermi satellite and mention briefly some prospects for the future. Okay, so some motivation. I am probably preaching to the choir here in terms of motivation, but still it's worth mentioning that quantum gravity is a holy grail for physics. You don't need too much pushing to be motivated to try and unify in a self-consistent theory Einstein's general relativity, which dominates on the large scales, and quantum theory, which dominates on small scales. So it's important in this context to mention the Planck scale, which all of you are probably familiar with, which is basically the scale at which one expects quantum fluctuations on the structure of space-time to become large. So one can derive them using three important basic physical constants. Planck's constant or reduced Planck constant h bar, Newton's gravitational constant g, and the speed of light in vacuum c that can be attributed to Einstein's special relativity. And you can see here in this simple diagram, which I downloaded from the internet, that taking various limits or various combinations of these constants, you can reach various limiting cases from Newtonian physics, special relativity, general relativity, quantum field theory, classical quantum physics, and so on. And at the center of all of these is quantum gravity, which involves these three important constants. So it is basically at the heart of physics. So it's very important, and there are many models and ideas out there. We've heard, some of us at least heard many of them in this ongoing meeting on quantum gravity. And it is very important to obtain some experimental constraints on these theories which could guide us. Okay, so how do we do it? I'm going to talk here about astrophysical constraints. So that's by no means the only way to try and constrain quantum gravity. One can try and do laboratory experiments or look at cosmology, etc. But experiments in the laboratory are limited. We can only reach certain energies. We can only construct an experiment of a certain size, etc., etc. However, in astrophysics, we get very large energies and very large distances practically for free. However, it comes at a cost. The cost is that it's not a controlled experiment. So we don't build the experiment ourselves. We don't know exactly what are all of its properties, and we can't repeat an experiment. So these are the advantages and disadvantages, but still one can benefit from using astrophysics to try and constrain quantum gravity. Okay, so I'll mention here very briefly some ways in which one could use astrophysics. There are many, many ways. There is no way that I could put on a single slide the complete list, so I'm not even trying. I'm just giving some examples. Okay, the first two examples in green are ones which I would talk about in somewhat more detail. I'll just briefly mention vacuum birefringence and vacuum dispersion of photons. There are also effects involving violation of Lorentz invariance, which could move the energy threshold for some interactions, such as pair production, where two photons produce an electron-positron pair. That could be probed through signs of attenuation of high-energy photons from a distant astrophysical source on the way to us with the extragalactic background light. So they can pair produce or not on the way. And if they do pair produce, then fewer of them would reach us and we could see it. That's one way. We also have possible Lorentz invariance violation of electrons, which can be probed from synchrotron emission by relativistic electrons, say from a nearby source such as the Crab Nebula. Other examples are space-time fuzziness, which could cause the blurring of images of distant sources or broadening of spectral lines. One could also use ultra-energy cosmic rays or neutrinos, where their energy spectrum could give us important information in that context. And also, if we have short transient events such as gamma ray bursts, then we can compare the signal in low-energy photons to that in ultra-energy neutrinos, when hopefully sometime soon we would detect them from GRBs. And then from time delay or lack thereof, we can learn about the propagation speed of the neutrinos on the way to us. Massive gravitons could, in principle, in some models, be formed in supernova explosions and affect what we see from these explosions. We could probe that in this way. Cosmic strings would have signatures in gravitational lensing or gravity waves. And the early universe could provide a lot of constraints as well, from CMB polarization or 21 centimeter neutral hydrogen line and so on. So I will concentrate mostly on vacuum dispersion from all of that, and just a few words about vacuum birefringence. But remember that there is much, much more to this field. Okay, so now narrowing the scope down, I would start with vacuum energy dispersion or birefringence. I would mention that in some models or theories of quantum gravity, you can relate between the two. So you can say if you want dispersion, it has to come with birefringence. In others, it doesn't have to. So if the two are tied together, life is easier for the experimentalists because it's easier to observationally constrain birefringence, as I will discuss soon, but in some others you cannot, so it's also very good to independently constrain dispersion by direct time of light measurements, how long it takes energetic photons from distant sources to reach us. Okay, so here we're probing basically one aspect of violation of Lorentz invariance, or LIV, Lorentz invariance violation, dependence of the speed of light in vacuum on the photon energy. And the simple way to parameterize this in a relatively model-independent way is simply to write down a general dispersion relation where all Lorentz invariance violating terms are expanded in a Taylor series. And here in this sum, we explicitly put S sub k as the sign of the effect. This coefficient can also be 0, and you don't have to have all the terms. Some others you have none or some or whatever. And there is a typical energy scale. So the photon energy over some quantum gravity energy scale, which we expect to be of the order of the Planck energy. And if you want to include the helicity dependence or vacuum birefringence, then there could be on top of energy dependence also helicity dependence, which would basically change the sign for the two different senses of the helicity. And we can derive from the dispersion relation the propagation speed, namely it's the group velocity, so we take the derivative of the photon energy with respect to the momentum to leading order, since the energies we actually measure of the photons are many, many orders of magnitude below the Planck scale. So we keep the leading order, and we get correction to the speed of light in vacuum. Here, c is the low energy limit of the photon propagation speed. And we call the leading order n, and we consider here n of 1 or 2, so a linear or quadratic leading term. Namely, we concentrate on the linear case because in that case our limits reach the order of the Planck scale. Even in the quadratic case, n equals 2, there are already many orders of magnitude below, and higher orders are even worse, the limits. And we will try to also constrain both possible signs of the effect, both positive sign where high energy photons propagate more slowly than low energy photons, or so-called subluminal case, and also the so-called superluminal case, a negative sign where high energy photons propagate faster than low energy photons. Okay. Now, for birefringence, a way we can constrain a possible helicity dependence is as follows. This basically means that we expect a different propagation velocity for right and left circularly polarized light or photons. And in this case, we expect a small difference from C to have the same absolute value but different sign. So one would get a relative shift in the phase of the circularly polarized light, so you can express some linearly polarized light emitted at some distant source as a sum of left and right-handed circular polarizations. Each one of these modes would propagate at a slightly different velocity, and therefore you would accumulate a difference in phase between the two equal to the angular frequency times the difference in their arrival time to us, delta t. And then you'd have a factor of 2 between that and the position angle of the linear polarization, which you would see. And one can express the difference in arrival time to us as the difference in their propagation velocity times their travel time, which is the distance over c. And one gets from here, because of the frequency that appears there, an extra power of the energy. So basically, it goes as the energy to the power of n plus 1. And again, we want to constrain n equals 1 because we get the strictest limits from there. So the way we do it is, if it were all exactly the same energy, then we just get the constant shift, and we'd still see linear polarization. We don't always know exactly in what direction you expect it to be at the source, so it's hard to learn something definite from that. But in most cases, we have a finite energy range because we want a finite number of photons to work with. And usually it's of order unity, so delta E is usually comparable to E. In this case, we have a difference in the position angle of linear polarization between two energies within our range, say at the lower end and the upper end of our energy range. So the difference is of the order of the shift itself, and therefore once this relative shift becomes of order unity, then you start to depolarize. Our polarization from different energies cancel out and leave only a very small residual. And that would be in contrast with measurement of significant degrees of linear polarization from astrophysical sources. And we can use that to set a constraint on linear polarization, on linear Lorentz invariance correlation. And one can see from here, basically, the delta T that appears in this place is similar to what we'd get just from the difference in arrival time of two photons, even if we didn't have helicity dependence, just energy dependence. But this can be sometimes very small and hard to measure. But since we want this angle to be of the order unity to start to detect the effect, and we'll be sensitive basically to time scales of 1 over the frequency, and at the frequencies that we measure, this is many, many orders of magnitude below what we could measure in actual arrival time of photons. So even in the optical, you have a frequency of 10 to the 14 or 15 hertz, so 10 to the minus 14 or 15 seconds is extremely hard to measure experimentally, so we could do much better in that sense. So to remember, one example is a distant galaxy at a distance of about 300 megaparsec from us with 10% polarization and optical. So a limit on the energy scale in units of the Planck energy was set to about 5 times 10 to the 3. Whereas from the Crab Nebula, a galactic pulsar wind nebula at a distance of about 2 kiloparsec, it's much closer than to us, but the measurements of polarization there were done at much, much higher energies, and even for n equals 1, because it's the square of the energy, so one could do much better. There were tens of % of polarization measured, and the limit was about 10 to the 9, so you could really get very, very good limits that way. Okay, and one could apply it also to gamma ray bursts, which are cosmological distances, so somewhat further away. From optical polarization, you can get several millions. And from polarization at soft gamma rays, you can get as high as 10 to the 15. But the main problem there, and people from outside the field are not really aware of that, is that most people in the field don't believe this polarization measurement. To measure polarization at hard X-rays or soft gamma rays is extremely hard experimentally. So most people in the field are really skeptical about this measurement. And of course, if you don't believe the measurement, you can't believe the limit. Okay. So now for vacuum dispersion. For that, we need time variability. So this is relevant mainly in the cases where the leading ordered term doesn't have birefringence, but only dispersion. And good candidates to start constraining that are TV flares from AGN, active galactic nuclei. You see here some nice images of AGN. These are accreting supermassive black holes at centers of galaxies with the black hole mass roughly between 1 million and 1 billion solar masses. They produce nice narrow jets with Lorentz factor of the order of 10 or so. And they can live millions of years, but sometimes they produce relatively short timescale flares, which are the most useful for our purposes. Here you see an example of a flare from July 9, 2005, observed by ground-based PV Cherenkov telescope, MAGIC. And you can see here the light curves at different energies from high to low energies, going from the bottom to the top, where they're fit with pulses peaking at different times on the plot on the left, and they're forced to peak at the same time on the right. So you see a better fit on the left, but the significance is not overwhelming. So they basically claimed either a possible detection at the level of about 3% the Planck energy for the linear case and 6 times 10 to the 10 GeV for the quadratic case, or alternatively, if you view it as a lower limit, so it's slightly less constraining, but within less than a factor of 2 in that tentative detection. So my view on that, well, for now, we have by now better limits, so we know it can't be due to propagation effects on the way to us. So if it's real, it's likely to be something intrinsic to the source, so we should remember that we can have effects intrinsic to the source as well. It's not a clean experiment. It's a complicated astrophysical object. Okay, another flare from an AGN was detected by Hess from TKS 2115-304 at a slightly larger distance. I forgot to mention the previous one was at a distance of 114 megaparsecs. This one is for 180, so somewhat larger. The energies are similarly TV energies, and the limits they got in 2008 are already stricter, about 6% of the Planck energy in the linear case and 1.4 10 to the 9 GeV in the quadratic case. But last year they came out with a paper that used the more sophisticated analysis techniques, and they were able, thanks to that, to improve their limits by a factor of 3 or 4. Respectively. And here you see the bright flare they used, which had several peaks. Here you can see it at different energies. You can clearly see correlation. You can also see it's not perfect, but still this can be used to constrain possible energy dispersions or a systematic difference between high and low energies in the time structure that we see. And here is a spectrum which is consistent with a simple power law. Okay. So now I'll move to gamma ray bursts, which is the main part of my talk. And first, I'll try to motivate you why gamma ray bursts are good for putting observational constraints on a possible energy dependence of the speed of light in vacuum. This idea of using gamma ray bursts for this purpose was suggested originally by Melino Camelia et al. In a Nature paper from 98. Giovanni should be here somewhere in the crowd. He's there in the corner. Okay. So that was a very, very good idea, which turned out to be very successful, probably in less time than the originators of the idea thought at the time. So astrophysical timescales to reach a Planck scale limit between 98 and today is not bad. Okay, the basic idea is very simple. We have a short explosion going on at the cosmological distance, gamma ray burst. It emits photons of different energies. So let's say 2 photons are emitted simultaneously or almost simultaneously at the source. And then they travel a very long distance until they reach us. Here at the bottom left, you can see a nice schematic picture of the Fermi satellite, which we used for our observations. Now, even if there is a very small difference in their propagation speed of these 2 photons of different energies, since their light travel time to us is so large, then it would accumulate to an observable difference in their arrival time to us. So we have a very large lever arm because of the large distance to the source. That's the basic idea. Besides that, GRBs are very bright, so despite being so distant, and still we see them as bright sources with many photons. They're short transient events, so short timescale is also a big advantage for this. I mentioned that they're far away cosmological distances, and also they emit high energy photons. So the gamma rays that we need, because the effect increases with photon energy. So almost everything we could think of for such a direct experiment is favorable with these sources. Okay. So since we rely a lot on these sources, then it would be good to say a few words about what these sources are, because they're not very simple, so it's good to have a handle or an idea of what we're dealing with. what is our experimental setup, if you will. Okay, so here you see a very schematic diagram of what a GRB might look like in a heuristic way. So first of all, you have a central source. Now, GRBs are divided into short duration and long duration GRBs. By now, we know that they're caused by different progenitors, a different processes causing them. We know that long duration GRBs are caused by the death of certain massive stars. They're associated with core collapse supernovae. Whereas we're still not sure what causes short duration gamma ray bursts. The most popular candidate is the binary merger of two neutron stars or a neutron star and a black hole. But by no means do we have any strong proof or evidence for that as we do for the progenitors of long duration GRBs. Okay. Now we know that the relativistic outflow or jets that produces the gamma rays that we see has to reach a Lorentz factor of the order of 100 to 1,000 in these sources. So they have to accelerate to highly relativistic Lorentz factors. How they do it is still not clear. There is the famous fireball model where the acceleration is thermal, but a viable alternative would be magnetic acceleration. Then at a certain distance from the source, they produce the gamma rays. They can't do it too close because then the system would be optically thick and the gamma rays wouldn't reach us. They have to do it at a place where the gamma rays can escape and reach a distant observer. Exactly how the energy is dissipated within the relativistic outflow and produces the gamma rays that we see is still not clear. A popular model is internal shocks or collisions between different shells in the outflow. That's one option. We're not sure. And even the emission mechanism of the gamma rays is still not clear. There are many candidate mechanisms, and it's still being debated. Now, with an even larger distance from the source, this relativistic outflow sweeps enough of the external medium to start and decelerate. So it drives a strong relativistic shock into the external surrounding medium. And then electrons that are accelerated in this shock emit synchrotron radiation, which lasts over a long time as this external shock going to the external medium gradually decelerates, producing the gamma ray burst afterglow, which can last for days, weeks, and months in X-rays, optical, and radio. So that's our general picture for gamma ray bursts. Okay, now our main tool for the observations is the Fermi Gamma Ray Space Telescope. You can see a schematic picture of it on the top right. It was launched on June 11, 2008. The first month or two were used mainly for calibrations on orbit and so on. But from about August that year, it started taking data in its usual operating form. And it has two main instruments. It has the gamma ray burst monitor, or GBM, which consists of two types of detectors, 12 sodium iodide detectors with an energy range between 8 and 1,000 keV, and two bismuth germanate detectors between 150 keV and about 40 MeV. It has basically full sky coverage, but in practice, since it's at near Earth orbit, at any given time, the Earth occults about half of the sky, so it views about half the sky at any given time. Okay? And in terms of sensitivity, it's comparable to its predecessor called BATSI, but it has a larger energy range, which is an advantage. And the main instrument that helps us on Fermi is the Large Area Telescope, or LAT. It has an energy range between about 20 MeV to over 300 GeV. Field of view, which is fairly large, about 2.4 steradians, and much more sensitive and has less dead time than its predecessor. You can see here on the bottom left how the fields of view of the GBM in red and the LAT in gray compare to the Earth. So about half the unocculted sky is covered by the LAT. And the LAT never observes the Earth, so it observes the unocculted sky. So in half the cases when we detect a GRB, it's within the field of view of the LAT. And you can see here on the bottom right a typical spectrum of a gamma ray burst and how well it's covered by the energy range of these two instruments on the Fermi satellite. Okay. Now, this is a real picture of the satellite before it was launched. You can see here on the top the LAT, the Large Area Telescope. You can see here the two different types of detectors and the GBM, the Gamma Ray Burst Monitor. And just a few words about the LAT, which is the main instrument. So basically, it has the 4x4 array of trackers. And the idea is first you surround it by an anti-coincidence shield. Then you have foils for conversion. You have a high-energy gamma ray coming, and within these foils producing an electron-positron pair, which then produces a shower, and then you can track the various charged particles in the shower and reconstruct both the direction of arrival and the energy of the incidence photon. And you want to veto cosmic ray events and so on. And for that, you have the shielding and the anti-coincidence detector, which surrounds the whole lab. Okay. Now, how do we use this to constrain vacuum dispersion of photons? So one can consider high-energy photons and low-energy photons from a given gamma ray burst. We call E sub h or L the high and low energies of these photons. And we want to constrain both possible signs of the effect, both subluminal and superluminal cases where high-energy photon propagates more slowly or faster compared to the low-energy photons. And the somewhat scarier formula here for the time difference of the arrival of two such photons is very similar to what we had before. So basically, apart from 1 over the Hubble constant, which multiplies here some cosmological term, which basically gives us the cosmologically corrected effective distance to the source. All the rest is basically the difference in their propagation speed in units of the speed of light. So by now we know the cosmological model reasonably well, so that's not a major source of uncertainty. It's a level of maybe a few percent by now, not bad. So we can directly relate this observable quantity, difference in arrival time, to this quantum gravity energy scale, which we want to measure or constrain. Now, it's important to mention, and if you look here at the bottom, the two photons don't have to be produced exactly at the same time and at the same place within the source. All we really want to constrain is propagation effects between the source and us. So you can see here an example of two possible emission locations within a schematic diagram of the source. So what we care is we want to compare what would be the difference in the arrival time of these two photons to an observer which stands very close to the source and suffers no significant propagation effects compared to us, a distant observer. This is to get at the propagation effect between the source and us, which presumably are due to the Lorentz invariance violation we want to measure or constrain. So really what we need to constrain in terms of the source is the difference in the emission time of low energy and high energy photons. It's important to keep in mind. And another important point is that basically we measure whatever happens between the source and us. So this difference in arrival time due to propagation effects is not necessarily only due to this specific effect you want to measure, but any exotic effect you can think of along the way would also be measured. We measure the cumulative effect of everything that happens within the source and along the way to us. Good to keep in mind. Okay, now we have a few different methods we use to set our limits. The first method, method 1, is as follows. It's demonstrated that using the diagram here at the bottom. So think about some finite duration emission from such a gamma ray burst. We show schematic flux as a function of time. It's important to mention that this method probes only the positive sign of the effect, where high-energy photons propagate more slowly and therefore arrive later compared to simultaneously emitted low-energy photons. And in this case, we measure pH, the arrival time, observed arrival time of the high-energy photon. What we do not know is what was the actual emitted time, where here we call that the time at which it would arrive if it would propagate all the way to us at C, if we had no energy dispersion along the way. So since we don't measure that time directly, we don't know it directly. But what we do measure directly is the arrival time of the low-energy photons, whose Lorentz invariance violation induced shift in arrival time should be negligible. And then since we know it's a one-time event, it's very reasonable to presume that the high-energy photon was not emitted before the explosion went off. So basically, if we say its true emission time was sometime after the explosion set off, after we start seeing some low-energy photons, then this is a reasonable conservative assumption, and therefore we can constrain this unknown difference between the emission and arrival time by this probably larger and more conservative time between the onset time of the relevant emission episode and the actual measured time. These are two measured quantities that we can work with. Okay, that's the basic idea, and now we applied it first to this bright long duration gamma ray burst, 080916C. Basically, this gives you the year, first two digits, a month, middle two digits, and day in the month when the GRB occurred. So basically, you can see from here that this occurred very shortly after the satellite became operational. Barely a month after it started, it finished all its calibrations and so on. So you're really happy to work with it. Here you see light curves at different energies. The lowest energies are at the top, green. You see 260 keV to 5 MeV. You can see here different energies as well. You can see here the bottom three are LAT. We have raw events, which are basically all events including and dominated by the lowest energy events of a few tens of MeV, for which the reconstructed direction and energy are not that great. So it's hard to use them for a spectrum, but just for the light curve, their statistics, or their number is much, much better. So we see a clear, sharp spike there. And here we see cleaner events above an energy of 100 MeV and at the bottom above an energy of 1 GeV. And the highest energy photon in this event is the one here you see with the arrow. It arrived 16.5 seconds after the trigger at the onset of the low energy emission from this gamma ray burst. And if we use in a very simple way the method I just described to you, using its energy of 13 GeV, the time after the trigger time, onset time, and the redshift of this burst, which is about 4.3, then we get the limit of about 11% the Planck energy, which was the best at the time. Not by a huge amount, but still within an order of magnitude of the Planck scale, which was very nice. However, less than a year later, we had this amazing short duration gamma ray burst, which was very bright. And despite being at a slightly lower redshift of about 0.9, in terms of distance, it's not a very big loss. But we gained much, much more by the fact that it's short duration. Altogether, most of the emission, look at the time scale here. So the format of the 5 panels here is the same as the one on the previous slide, which I showed you, showing light curves at increasing energies as you go from the top to the bottom in the different colors, same color scheme. And you can see at the top individual photons. So you can see their energy in a logarithmic scale as a function of their arrival time in a linear scale. So you can see if you look at the lower energy light curve in green here, there was some small blip in the beginning, precursor, then half a second, nothing, and then for the next half second or second, most of the emission. So basically, there was a small blip that barely triggered the GBM, and then the main emission took more or less less than a second, not much more than that. So it was very short, which is a big advantage. On top of that, the highest energy photon, which you can see here, had an energy of about 31 GeV. So that was very helpful, and it arrived about 0.83 seconds after the trigger time here. And since we built a lot and that one photon, then we really went through a whole lot of effort to make sure, one, that it's a photon, two, that it's physically associated with a short gamma ray burst. So it's amazing the number of working hours that people in the collaboration devoted to analyzing that one event. But we made very, very sure that it's a good, clean, reliable event. It's a photon and associated physically with this short GRB at a significance of over 5 sigma. So we're pretty sure of that. So we can use it. Okay, and then we conservatively used the 1 sigma lower bound on the energy of that photon and on the redshift or distance to this short gamma ray burst. And I just want to mention in this context that there are some intrinsic spectral lags known in GRBs at MeV energies, or say between 10 or 20 keV to about an MeV. But these are usually seen on timescales of no more than the width of a single spike. You can see here, there are spikes here that are typically not more than 10 or 20 milliseconds wide. So even if we had some intrinsic dispersion at that level, it wouldn't really significantly affect our results. It's important. And even if you had intrinsic dispersion, then to exactly cancel out a totally independent effect and to do it independently in different spikes would be too much of a coincidence and fine-tuning. Okay. Now we applied our first method here, and there are various possible choices of the relevant low-energy emission time or start time that we could use. The most conservative one is to use this small blip or precursor I told you about. And then if you use the onset time of that small blip or precursor, then you get 1.2 times Planck energy, already above the Planck energy for the linear scale. But if you really believe that that very energetic photon was emitted there at that small blip, then for any reasonable emission spectrum, or if we take the observed and measured emission spectrum for this particular gamma ray burst in particular, then we would have an association with such an energetic photon a much larger number of lower energy photons, say of the order of 100 MeV or so, which would have much smaller energy dispersion and therefore would mark the emission time of that high energy photon. And in particular, they would be accumulated along this solid black line here if they're emitted together and just suffer this linear or quadratic energy dispersion for these two lines that you see there. And since we do not see anything accumulating there, this makes it highly unlikely. So it's much more reasonable that it was emitted sometime during the main emission episode. So if we instead use a start time as the onset of this main emission episode, in particular, the one in red here for ALAT events are pretty much corresponds to the lower energies as well. That would give us about 3.4 times Planck energy, a stricter limit, but still reasonably conservative and reasonably robust. One could make slightly less conservative assumptions on the starting time to associate it in a similar argument with photons above 100 MeV, and we have a fair number of those. That would give us about 5 times Planck energy, and if we associated with photons of about 1 GeV, that would be now, went over the green and now blue lines here, that would give us about 10 times. That's still reasonable and not very speculative, so I would put a decent amount of money that one can trust that. Okay. Now, that was our first method. For linear case, basically, this was a relevant line here. About a year after we came out with this result, there was a paper that came out claiming they saw some small precursor about 13 seconds earlier. So before here, between here and there, it's about half a second, so it would be somewhere around the end of the room. They presumably saw a small precursor there. You can see here one satellite SWIFT. It sees maybe a small blip here, another instrument didn't, but then SWIFT has better directional information, so maybe it could see something the GBM, which has a much poorer angular resolution, could not see. So it could indeed be real, but I argue that even if it is real, from similar arguments, it's very unlikely that this 31 GeV photon was emitted in association with such a precursor. The reason being as follows. One, as I mentioned before, if the 31 GeV photon would be emitted there, then it would be accompanied by a large number of lower energy photons that would mark the true emission time, and Fermi was observing there and did not see anything. That's one thing which is very unlikely, and it would require another very unlikely thing to happen, which is namely that it would fall smack on top of the half-second brightest emission episode, and not only that, but on top of a very narrow spike seen here at all energies. So if you take the whole time covered by such narrow spikes and divided by these 13 seconds, it would require a large degree of fine-tuning. So you need two unlikely things to happen for this photon to originate at that small precursor or blip. So I find it very unlikely, so I don't think it has any significant effect on our result. But I wanted to mention it nonetheless. Okay. So now to a different and least conservative limit. So here we try to associate this highest energy photon with this narrow spike that you see here, basically at all energies. So it's very narrow. Basically, this gray line here that goes through all energies is 10 milliseconds plus minus on either side of that photon. Falls smack on the middle of this spike. And if we argue that it's physically associated with it, and we can constrain the LIV-induced time dispersion to be no more than 10 milliseconds, it would give us about 100 times the Planck energy. But it's not as robust as the other limits. The chance probability is non-negligible, around 5%. If you want to be more conservative, maybe even 10%. So at best, at the 2 sigma level. So one should think of it with a big grain of salt. But still, if you had to bet your money, and the betting ratios are 20 or 10 to 1, you'd better put your money there and not on the other side of the bet if you're a betting person. Okay, so it still has some relevant information. We try to do something similar on another photon on this small precursor, but it's much less constraining. Okay, the third and most robust method we call DISCAN dispersion cancellation. It's based on the lack of smearing of fine structure. As you can see here, there are very narrow spikes here seen across all energies. If you'd have significant energy dispersion of either sign, it would tend to smear out the variability. So from the fact that it was not smeared, we can limit the dispersion. That's the basic idea. We used the brightest portion of the burst with very strong variability, a wide energy range. We used events from 35 MeV up to 31 GeV, actual measured energies. So we have there some 3 decades in energy, and it's an unbinned method, unbinned in energy or time, so we don't lose valuable information. The idea is to take a trial function for the energy dispersion, linear in our case, and then the magnitude is left as a free parameter, and then you try different values and see which of these values maximizes some measure of the variability of the light curve. And then since dispersion tends to decrease and not increase variability, then the value that maximizes the variability is probably the closest to the true one, and you can, in this way, limit dispersion of either sign. We got a more or less symmetric limit, which at 99% confidence level gave us delta E over delta T of no more than 30 milliseconds per GeV, which corresponds to an energy scale or mass scale of 1.22 times Planck mass or energy. And it's very robust, so even if we take out all photons above 3 or 1 GeV, it doesn't change much. It uses hundreds of photons, so this is really hard to circumvent. Okay, so just to summarize the different limits from this short gamma ray burst, from this whole table, we look mainly at the ones on the linear energy dispersion. We have the first 5 limits are based on this single highest energy photon, 31 GeVs. So as I mentioned, we made sure it's real and it's from this GRB. And we have different limits from the most conservative to the least conservative, which range almost 2 orders of magnitude, depending on how conservative you want to be. Okay? And there's also this 2 different methods. One is just the difference between the onset of the 11th emission episode and the highest energy photon, first method. Second method is basically associating a high energy photon with a low energy spike. So it's the least conservative and the most robust for 2 possible signs of the effect is this dispersion cancellation or lack of smearing of spikes. Okay, all our limits are above the Planck energy. The most conservative ones are 1.2, but even ones up to 10 times the Planck mass are, in my personal opinion, reasonably conservative, even if not the most possible conservative ones. Okay, and now I would say something pretty controversial in this audience, perhaps, that I think that our results disfavor quantum gravity models with linear dependence of the photon propagation speed on its energy. That's partly a matter of taste, so this is my personal taste. And here is a table summarizing all limits we got for different gamma ray bursts with Fermi. So the first 2 I already discussed in detail. The first one, the long gamma ray burst, 0809 16C, we got about 11% of the Planck energy. Then the short one, and all the different limits that I already mentioned in much detail. So at the bottom of the table are only 2 other ones for which we got slightly worse limits compared to the first long bright Fermi GRB, Fermi lat. So we got between 6, 7, or 8% of Planck energy with those, but still it's worth checking and worth comparing results from different GRBs. These are color codings of the different types of limits I've explained to you. Okay. Now, there is some work in progress. As I mentioned before, you saw the example with AGN, that for the same TV flare from an AGN, the same group of the Hess collaboration managed to improve their limits by using better, more sophisticated analysis methods. So now we're trying to do something similar here. Back then, at the time, it was towards the end of the first year of Fermi operation. And the thing is that the first year, the data was proprietary. But then, after the first year, it became public immediately. So we had a very strict timetable, because if we would have waited after the data became public, we might have been scooped on this important result, and we really didn't want that. So we didn't have all the time in the world to use all possible analysis methods. We were fairly limited by time, but now we have more time to do various different types of analysis, very time-consuming, very carefully, but it's worth doing. So we're doing it, and this can and does somewhat improve the limits, though since it's still work in progress, I can't give you the new numbers, but only briefly discuss the different methods or different approaches. So we're using three different approaches. One of them is the pair view, basically taking all pairs of photons within the relevant time interval, ordering them according to their observed time of arrival, and then taking their difference in time arrival compared to the difference in their energies to the appropriate power of n. And then the idea is that the most common time difference would be, or time over energy to the appropriate power, would be that associated with any intrinsic lag. So you would get a peak at that value of tau sub n, delta t over delta e to the appropriate power. And it would be centered on 0 if you have no lag. If you have an intrinsic lag, it would be sort of centered around that. And you can estimate a confidence interval from that and so on. I don't have time to go into the details, but this is the basic idea. So it's somewhat different than complementary method, and you don't do any binning, so you don't lose important information. And that can be very nice. The second method is sharpness maximization, and the idea is very similar to the dispersion cancellation I mentioned before, so I wouldn't elaborate on this much more. It's a slightly different realization of a similar idea. And finally, there's likelihood analysis, which was used already in AGN, and it is based on modeling the low energy part of the light curve to produce some template and modeling the observed spectrum, and then using that as a template to calculate an unbinned likelihood for the high energy events or photons from the data, and then trying to maximize the likelihood and obtain the best fit value plus confidence interval in this parameter tau sub n. Okay. So we're working on that. And finally, some prospects for the future. So this is the CTA, the Cherenkov Telescope Array, the next generation TV ground-based observatory. It's a very big project. And the energy range would be between roughly 20 GeV or so, maybe slightly lower, to hundreds of TeV. And it would represent an order of magnitude improvement in our sensitivity compared to current ground-based Cherenkov telescope instruments. It would have better energy and angular resolution as well. This involves already more than 1,000 members in this consortium and 27 countries, still counting. And the preparatory stage is probably about to finish in the next year or two, and then it would start being constructed and maybe start being operational 5 years after construction starts. The idea is to have two sites, one in the southern hemisphere, one in the northern hemisphere, and altogether it would have hundreds of telescopes of 3 different sizes, so there would be large, medium, and small size telescopes altogether. So kind of how it might look like. Okay, for transient sources such as the GRBs, it would in particular reproduce a very large improvement in the effective area. A typical long-duration GRB is of the order of a minute, so you can see here a comparison of the sensitivity with Fermi compared to CTA. You can see that at a few tens of GeV, it's about 4 or 5 orders of magnitude higher effective area, and that's a lot. And this is energies that we actually detected from GRBs. If you remember the 31 GeV photon from that short GRB, so we actually detect such energies. If we'd be able to observe a similar GRB with this new instrument CTA, then such a much larger effective area means we would detect many, many more high-energy photons, so we could do much, much better with that. Okay. Now, for prospects with CTA, so briefly mentioning the different methods that we've used. So method 1, just using the single highest energy photon in time from the onset, is probably not very promising, namely because the typical response time to slew the instrument in the direction of the GRB is of the order of half a minute. So even if you have TV energies, then you could reach comparable sensitivities to our current most conservative limit, but it's hard to do much better. And also intrinsically, TV energies, if you have a distant source, then first intrinsically you have fewer such photons, and then attenuation and the extragalactic background light on the way to us might start being an issue. Therefore, the third method, discount dispersion cancellation, is probably the most promising one. And as we see here on the light curve of long Fermi-latch GRB, even in that case, we see occasionally some very sharp spikes. And if we have very good photon statistics and such a spike, so we could be triggered early on because it's a long GRB, then we have an instrument looking in that direction. When a sharp spike occurs, we could do much, much better. Simple estimates of, say, a tenth of a second variability time over energies of roughly 0.1 TeV, which are fairly modest, would be a factor of 30 improvements. We could probably do better than that. And if we happen to observe a short GRB in the field of view, so it has to be in the field of view if you want to catch a short GRB, because you can't slew it in less than a second. But then we'd probably do some survey mode. Since we have many different dishes, we could point them at slightly different directions with slight overlap, but altogether covering a much larger field of view. In that case, our chances of having a short GRB within the field of view increase dramatically. And if that happens, then a variability timescale of, say, 10 milliseconds, we could in principle do even better, and energies of 1 TeV could give us 1,000 or better improvement compared to current limits. So there is a lot to look forward to. Okay, just to conclude, astrophysical tests of quantum gravity can help. Try to look for them. They can be in all various shapes and forms. So try to talk with different experimentalists, astrophysicists, observers, whatever. It can be fruitful. In particular, GRBs can be very useful, and bright short GRBs are much more useful than long duration ones for the reasons I mentioned. As for our limits, then our most robust and conservative limit is 1.2 times the Planck mass for linear energy dispersion. And still conservative, but slightly less robust limits are up to 10 times the Planck mass, and our least conservative one, our intuition builder, is about 100 times, but has a non-negligible chance probability. So take it into account, of course. And altogether, I view this as quantum gravity models with linear photon energy dispersion being disfavored by our result. Thank you.
Students, first chance at questions. So if there's any students that have questions. No? Okay, well then we can throw the floor open to questions from non-students.
So first of all, this is much better. I mean, maybe Giovanni can speak for himself, but I think that back when we first began thinking about these kind of experiments, testing Lorentz invariance violation or deformation, we never dreamed it would be this good this fast. So there's many congratulations to you and your team to be at least at the Planck scale, if not 100 times over the Planck scale. So I just have a question about methods. None of the methods utilize comparisons between different gamma ray bursts. Have you given any thought to looking for redshift-dependent systematic lags? Maybe if you had.
We have given thought to that. The point is, one, we don't have any measured lags yet. We only put limits. That's one point. And even then, for combining different gamma ray bursts, so I showed you a table with 4 different gamma ray bursts, so maybe I can quickly go back to it. The point is, it's dominated by this short burst. As you can see, all the rest, even compared to the most conservative limit, all the rest are at least an order of magnitude below. So we tried, but then you end up being dominated by that, and all the rest currently don't change the picture much. So we're not seeing any systematic dispersion. Once and if we see systematic dispersion, then of course we would try to compare different bursts and see if it matches expectations or not. But currently we're not even seeing any clear signal. We can only put limits on such a signal.
More questions?
Lee told me that he asked you already, had an opportunity to ask you. Maybe I can ask you here with everybody. You used these 4 bursts were all seen. I mentioned in my talk they were all seen in the first 13 months of operation of Fermi. So, and you have to give me credit for telling you this. Only 24 months into operation in Paris, I told you, isn't it strange that? So how now you were not impressed then, but isn't it strange that we still have these 4 bursts to show? And is the collaboration having any ideas? It's still bad luck. You told me in Paris it was bad luck 2 years ago.
Right.
The luck is running bad still.
So that's kind of a sensitive question. So if you look at it from the cold statistical point of view, it's not a huge fluke, probably. So probably we were kind of lucky in the first year. And if you look at the dates here, so those 2 were kind of a bit more than a year after the start of normal operations. So yeah, we were lucky that in the first year and something, we had really 4 very bright, nice ones. We actually had a few that came close afterwards, but probably psychologically, since they weren't the first and they were slightly less bright than those, even though not by far, then they made much less noise, and you hear about them much less. That's one point. So the fluke is not as large as you might think, but still, yes, of course, we didn't get such nice events from this last of the 4 until now. But I believe that if we wait enough, we're bound to observe more bright bursts, and we will. So we probably had some good luck in the beginning, bad luck now, and hopefully our luck would change for the better sometime soon. So the instrument didn't deteriorate or anything. Quite to the contrary, now, after it's already in orbit for some years, then we know the instrument much better, and our ability to reconstruct events has improved. And not only that, but everything is recorded. So even though a burst like that already happened some years ago, everything is recorded, and once we learn the instrument better and can better reconstruct events, we can go back, go over the same GRBs, and recover events that we didn't identify in the first place and do somewhat better. So even that we can do. So the actual deterioration in the abilities of the instrument are fairly negligible. I would say, if anything, we learn to work with the instrument a bit better. So it's not the fault of the instrument. It's probably nature that's being a bit cruel to us now. Maybe it was a bit generous to us in the beginning, but it must even out eventually.
I have a comment regarding what you showed us, because we saw the start that you have very strong constraint on birefringence, right? If you assume birefringence, you can get up to 10 to the minus 15, let's say 10 to the minus 10, 10 to the minus 15, depends. The 10 to the minus 15 was controversial, but still is much stronger than what you get.
Yes, I wouldn't rely on that.
Well, let's say 10 to the minus 10, 10 to the minus 10 would be conservative. Then I think one point that should be stressed is that if you take an approach within effective field theory, at this level, linear violation of Lorentz invariance, then you would expect birefringence. So if you see a signal from from this kind of observation, from this second set, it would be signifying that basically you are not in an effective field theory framework. It would be a signal that the effective field theory framework for dealing with a systematic taking into account the Lorentz violation, would fail. So in spite of the fact that the search for dispersion in gamma ray burst can be seen, for providing constraints which are weak with respect to the one that you can get from birefringence, that should be there in an effective field theory framework. I think it's important to stress that it's still worth looking in this independent way, because if you find anything, then it would be of dramatic consequence.
Yes, one could view it in this way. Well, by now.
You see, you in your presentation, you are very phenomenological.
Here,
yeah.
yes.
But in a certain sense, in the standard model extension, at that order, linear order, they are CPT odd, and you would have birefringence automatically.
I know.
So if you...
Part of the reactions I got is, of course, people who believe in that, they said, of course you didn't detect anything and just put some limit. We know that already because of that. But
what I'm telling you is that I believe in that, in the sense that I worked in the effective field theory framework, but I'm supporting you in searching for this, because it's a way to see if it's consistent.
Exactly. So there are all these things you believe in, but it's good to test it, because this is science, right? So you want to rely basically on experiment and measurements rather than beliefs. So I'm happy that you think it's indeed a good idea to look for this direct time of flight effect.
But to say it even stronger, the Lorentz these two experiments between them distinguish broadly between Lorentz invariance breaking, which would lead through the effective field theory picture to expectations of seeing the birefringence, and to distinguish between that and Lorentz symmetry deformation, which doesn't fit into the effective field theory picture and would lead you to expect a parity even effect. And you see neither.
Yes. So I definitely agree that it's good to test both independently.
So maybe I can make an observation. As kind of a snarky observation is that you said in the last slide that you've ruled out models of, quantum gravity models at Planck.
I didn't say rule out. I said they're disfavored, and I mentioned that that's my personal taste.
Yeah, but so let me finish my observation. So I think the things that you rule out are that don't seem to have any quantum or gravity or model in them.
Oh, this is dangerous ground. You call here models or not with the crowd. I mean, since I'm not behind any of these models, and I'm not the one to defend it, maybe other people in the crowd would wish to defend them.
Well, okay, so they are models, but they don't have quantum or gravity in them. So that's.
And I thought I was being controversial.
Okay, well, are there any further questions? Okay, then let's thank the speaker again. So I believe high tea will be available shortly downstairs in the bistro. There will be no colloquium next week. The week after, we'll have a colloquium that's November 7th, I believe, with Jaume Cuejo.